Okay, these are the notes for Algebra 1 8.6 where we are comparing linear, exponential, and quadratic functions. So basically, we have actually now already learned these three functions. So here we have a linear function. So a linear function is y equals mx plus b. We know that. We've done that a million times. That's how the format looks. It can also be, keep in mind, in standard form. We've learned that one. And then also it could be in point slope form. But in the end, all of them can be rewritten as y equals mx plus b. And a linear function is a line, and we can tell the graph. The graph is any straight line. It just cannot be vertical, because if it's a vertical line, it is not a function. So not a vertical line. That's kind of the only limitation on which lines are not okay. Horizontal is okay, vertical is not. All right, exponential. We learned this in chapter 6, right at the start of the semester. So exponential function is going to be y equals a times b to the x. This graph is showing exponential growth. It can also show exponential decay, like this. And just kind of as a refresher, the a value right here is the y-intercept, or the starting amount, where the b value is the growth of the decay factor. And then quadratic is what we've been working on this chapter. We know that we have that standard form. We also, of course, have vertex form. And we have intercept form. But all of them can be rewritten in standard form. So that's why they list that one. And of course, it can open up or open down or have any type of transformation. Okay, when you're identifying them as points, you just go ahead and graph them. So if we real quick graph, we have 4, 4. 2, 0, 0, 0, 1, negative 1/2, negative 2, 4. So when I look at those points, that's quite obviously quadratic. All right, go ahead and pause the video and graph the points on B and C, and then come back on and we'll go through them. Okay, so you can see that these points fall in a line, so therefore this is linear. And then you can see that these points are making an exponential curve. So we know it's exponential. Okay, so we're going to talk now about how to do the same thing, essentially how to tell if it is linear, exponential, or quadratic when we just have a set of points or a table. So on a linear function, what we do is we look at the first differences. And if the first differences are constant, then it is linear. Now I'm going to go ahead and jump down here to quadratic. Quadratic, we look at the second differences. And if they're constant on the second differences, then it is quadratic because the second row has a degree of 2, which means it's quadratic. Okay, and then how we tell the exponential is if the y values are in a common ratio. And we have done all of these things. We've done linear and exponential in previous chapters. We did linear in chapter 3 and in 6, and then exponential in 6. So let's see what this reads about. So when they talk about first differences, what they mean is you're going from the y values and you're doing the right number minus the number just before it. Always go in that order. So that makes negative 3. So do it again. The right number minus the number just before it. So 5 minus 8 is negative 3. Now you have to check all of them. 2 minus the number just before it, 5. 2 minus 5 is negative 3. And negative 1 minus the number just before it, negative 1 minus 2 is negative 3. So that's the first time I did it. So these are called first differences. So if the first differences are constant, then that means that it is linear. Okay, so if this first differences were not constant, I would do it again and find the second differences. And if those didn't work, I'd look into a common ratio. So like on this one, if I try the first differences and I do 2 minus 1, okay, that's 1. And if I do 4 minus 2, that's 2. And then 8 minus 4 is 4. And 16 minus 8 is 8. Those clearly are not the same. So that was the first difference, is they're not the same, so it's not linear. So if I do 2 minus 1, this is second differences. I'm doing it the second time. I get 1. 4 minus 2, I get 2. So right there, I know they're not the same. So this row tells me that it's not linear. This row tells me it is not quadratic because second differences didn't work. And so I'm going to try it again. I'm just going to write them here so that we don't have to erase everything. So how I can do the common ratio, okay, what I can do is I'm looking at, and if I look at instead, if I'm doing a ratio, if I do 2 over 1, so 4 over 2, instead of subtracting, you're dividing. 8 over 4, 16 over 8. I always take the right number divided by the one just before it. So all of these get 2. That means it has a common ratio of 2, which if it has a common ratio, that tells us it is exponential. All right, let's go look over here. So I'm going to try first differences first. Now I'm showing my work so you can see what order I do things in. But I understand if you're just putting these in a calculator. So I do -2 minus the number just before it. So it's minus -1. And that ends up with -1. And I do -1 minus the number just before it. So minus -2, that ends up with 1. 2 minus -1, that's 3. And 7 minus 2, that's 5. Okay, this is the first differences. And they were not all the same, so it's not linear. So now I try the second differences. 1 minus -1, that's 2. 3 minus 1, that's 2. 5 minus 3, that's 2. So these are the second differences, and they are all the same. And that means when they are all the same, that's what it means to be constant. Constant means they're all the same. So since they are all the same on the second differences, that tells me it has a degree of 2, which is quadratic. Okay. So the other thing we're going to learn about this chapter is we're going to have to compare functions using the average rate of change. Now, if you are in a nonlinear function like a quadratic or an exponential, rate of change is not constant. That's how it occurs, is because the rate of change varies. Constant rate of change means it's a line. So you can compare two nonlinear functions over the same interval. I'll explain that in just a second, using their average rate of change. An average rate of change is just the slope. All right, so we can compare using their slope. Okay, let's try this. So this says, 2 social media networks open their memberships to the public. Compare the network memberships by calculating and interpreting the average rate of change. Okay, when you see this, your brain should be like, oh, that's the slope from day 10 to day 20. This is the interval. And what they mean is when they say you have to use the same interval is it's not like apples to apples. If you say from day 5 to 20 on this network and day 30 to 100 on this network, that just doesn't make sense. It's got to be the same, like the same amount of time and the same actual time. Because if you were comparing like the startup of one social media network to like a month into another social media network, well, that's just not fair. So if I go day 10 to day 20, I have these 2 points on network A. So on network A, I have 10, 1400, and 20, 2150. So I want to find the slope. Remember, I do y2 minus y1 over x2 minus x1. So I end up with 75. And what that means specifically is that not all the time, but specifically from day 10 to day 20, network A increases, they gain their memberships 75 per day. On average, it doesn't mean it was exactly 75, but like basically overall from each day they gain about 75 people. That's the average gain. So then here, if I look right here, that's where 10 is, and here's 20. So I'm going to estimate points here. At 10, it is, this is going by 300s, right? So this is 900. It's just below 900, but not halfway. I'd say it's about 800. Keep in mind, each box is 300. So then this one right here, the second point at 20, is just below 1800. So I said maybe 1700. Okay, each box. The height of each box represents 300 members. So, I mean, that's quite a lot to take account for. Okay, so if you find the slope for that, you're doing 1700 minus 800 over 20 minus 10. And so you're getting 90. So what this tells us is that on network B, not at all time, just from day 10 to day 20, network B saw an increase of 90 members per day on average. That means some days may have been a little over 90, some days may have been a little under 90. That was just their increase at that time. Okay, so it says compare them. So, I mean, you can tell then that network B had higher growth. And just real quick, when they're talking about up here, how they said nonlinear functions, the rate of change is not constant. Let me show you a visual of this. What that means is like right here, if you go from day 0 to day 10, it'd be that line. But then 10 to 20 would be this line. Do you see how they have different slopes? So it's like it's increasing faster and faster. That's what they mean by not having a constant rate of change. Like that they don't have a common slope all the way through. Okay, look at example 4 real quick. So a team of researchers counts the number of sea turtle nests on an island and in a coastal life refuge. So this function right here is the ones on the island. Specifically, X represents the number of years after 1990. So out in the refuge, the team counted 1,275 nests in 1990. So keep in mind, X is the number of years after 1990. So this is the starting amount. And the nest increased by 6% each year. When you increase by a percent, that means it is exponential. Okay, so if I wanted to write, this is for the refuge. If I wanted to write a function, I'm using exponential, y equals a times b to the x. A is the starting amount. They started with 1,275 nests. B, remember, you don't just use 0.06, you do 1 plus 0.06 because it's growth. So you put 1.06 to the x. And so that's the refuge right there. So when they want to know the greater average rate of change. All right, so for the island, we're going to plug in 0 because 1990 is when x equals 0. It's 0 years after 1990. And for 2010, think how many years is 2010 after 1990? It's 20 years. So we're going to plug in 20 for x. So I'm going to use my calculator and I'm going to go into this equation for the island and I'm going to plug in 0 and I get 1,750. And then I'm going to plug in 20. I'm going to plug it in for x on the x squared and on the x right here. Okay, when I plug in 20, I get 4,790. So now if I find the slope to that, y2, minus y1 over x2 minus x1, I end up with 152. All right, and so that is essentially from 1990 to 2010, the island had an increase of 152 nests every year on average. So now we're going to do the same thing for the refuge. And so I'm going to plug in 0 to my equation, and I made right over here. And I'm going to plug in 20 to this equation. And I get 4,089, and then I'm going to find the slope. Okay, so I went ahead and found the slope. It was 141. So that means that from, not at all times, but from 1990 to 2010, the island has a greater average rate of change than the refuge. Now it says, which location will eventually have a greater number of nests? Because the refuge is exponential, eventually it will be a greater number of